Today we are going to discuss the second part of the chapter 4, and we will focus today in the concepts of heat, molecular theory, and specific heat. It's important to know that the heat and technology are inseparable. In these two pictures we can see how the heat, how using heat we can cutting and welding metals. For example, here we had slabs of the steel. In this case, we had plates of the steel, and this is important because the steel is used in many applications. For example, the steel is used in automotive, in appliance, and building industries. And now we know heat and temperature, they are not the same quantities. And temperature is based on the kinetic energy of the molecules. When we are measuring the temperature, what we are measuring is the kinetic energy of the molecules. But we know they are different. As we say, in this case, we had these two beakers with different amount of water. Then if the temperature is 100 degrees Celsius, we know in this case the temperature is the same. However, the amount of heat is different because we had twice amount of water. Now let's define heat. First, let's think in this situation. We are pushing a table across the floor, and then what we are doing is we are working against friction. When we are doing work on the table, we are providing energy to the table. And what kind of energy? The work we are doing, in what kind of energy is converted? It's converted into the kinetic energy because we can see the table is moving. But also another thing is the bottom surface of the legs become warmer. And what happened is part of this energy is part of the work we are doing on the table is converted into the kinetic energy, but part of this work is converted into heat. What happened is this heat is increase the energy of the molecules. This is why the legs becomes warm, because the molecules start moving faster. And this kind of energy is called heat, and that energy is called the internal energy of the object. Is the energy of the molecules. And this internal energy can be kinetic energy, means related to the translation, vibration, rotation of the molecules, but can be also potential energy, and in this particular case is called the chemical potential energy because it's related to the bonds between the molecules or the atoms. Then what is heat? Heat is related to the internal energy of the substance. Is related to the kinetic and potential energy of the molecules. Let's now see what are the units for heat. In the metric units, the units for heat are first calorie, and calorie we just abbreviate with cal, is the energy needed to raise temperature of 1 gram of water in 1 degree Celsius. Also, we had another unit that is mainly used to express the amount of energy in food, and is kilocalorie. And this kilocalorie also we can write in the same way we use calorie, but you can see here the C is the uppercase C. And this is why you have to be careful when you are reading the problems related to heat. if the C is a small or the C is big C. Because if it's a small, then it's related to this unit, but if it's big C, that calorie is equal to 1,000 small calories. So then means 1 calorie with big C equals to 1 kilocalorie. Then if we had calories with big C is the energy needed to raise temperature in 1 kilogram of water in 1 degree Celsius. Then we can see it's really different. Yes? For a small C is how much energy we need to increase the temperature in 1 degree Celsius for 1 gram of water. But in the second case is how much energy we need to increase in 1 degree Celsius the temperature of 1 kilogram of water. Then it's really different. But here we can see is we had 1 calorie big C equals to 1,000 calories with a small c, or equals to 1 kilocalories. And just be careful with this unit. The other units in English system is the BTU, which is British Thermal Unit. We are not really use much this one, but it's just I want this is the unit in the English system. And one more thing is important. We can see heat is energy. Yes, just is usually the units for heat we are given in the units for heat we are given is in calories, but because it's energy, then we can get also in joules. Yes, then there are one conversion factors we can use for that. Then this here is the conversion factor from calories to joules. Then 1 calorie equals to 4.184 joules, and if we multiply by 1,000 on both sides, then we can see also we can use this conversion factor. 1 kilocalorie equals to 4,184 joules. Then let's now try to solve this problem. Then in this case we had 1,000 kilograms. Car is moving at 90 kilograms per hour, means 25 meters per second. Then we want to know how many kilocalories are generated when the car brakes to a stop. And let's see what we know the problem. Then we know the mass of the car. It's 1,000. It's 1,000 kilograms. And we have and we know also the speed of the car is 25.0 meters per second. Then the question is how many kilocalories are generated when the car brakes to a stop. And what happened in this case, the car is moving, then the car has kinetic energy. Then we want to know if all the kinetic energy is converted into heat. Yes, we want to know is how much is this energy in kilocalories. Then what we need to do is we need to calculate the kinetic energy, which is the energy is converted into heat, but we need to find the kinetic energy in kilocalories. This is the units we need to give at the end. Then let's first calculate the kinetic energy. Then we had kilograms, we had meters per second, then the units are consistent, no problem. Then just now we will calculate the kinetic energy. Mass is 1000 kilograms and the speed is 25.0 meters per second. And here we need to square the velocity speed. And you can skip some of the steps. I will just try to explain all the steps. We need to square this velocity with meter squared second squared. Then here you can multiply 1000 times 625 and divide by 2. Or you can divide 1000 divide by 2 and then multiply. Either way, you will get the same answer. Then finally, you had 312,500 joules. Then now, because we need to convert this one into, we need to give the answer in kilocalories because they don't want the answer in joules. Then, because all the kinetic energy was converted into heat. Then let's now change this one. We know 1 kilocalorie equals to 4,184 joules. Then now and we are using this conversion factor because the problem asks in kilocalories. This is why. Then let's convert this number. This is joules. And joules cancel out, and if we divide this two, we will get 74.68. 74.68. Then now we can say the kinetic energy equals to 0.7 kilocalories. Here it's important to see in the book, in some cases, they just take into account the significant digits just of in the answer. For example, if we had here, if the information we had from the problem is 3 significant digits and 5 significant digits here, then they will give the answer with the less number of significant digits. And this is the way they are doing it in the book. Then it's okay if you are doing it that way. Just you can take, because usually now we will solve problems in which we had to complete several steps. Then what we can do is we can take into account the significant digits at the end. Then if we had 3 significant digits here, this is the less number of significant digits, then we will give the answer with 3 significant digits also. Now, just to review, we know temperature is based on the molecular kinetic energy of the molecules that make up a object or a substance, but heat is based on the internal energy of the molecules. And we say that internal energy can be kinetic energy, is the motion of the molecules, can be translation, can be vibration, they can vibrate, rotate, or can be translate, but also is related to the chemical potential energy. If the energy increase, this process is called heating, but if the energy is decreasing, then that process is called cooling. Now let's correlate these two quantities, heat and temperature. Then there are three variables that influence how much heat you need to bring a liquid, in this case water, to boiling. Then first is the temperature change. Yes, this is the first variable influence that process. The second thing is the mass of the substance, and the third thing is what kind of material we want to boil. As this is the three different variables influence this process. And let's try to correlate these variables. Then what happened if we increase the temperature? What happened with the heat? Yes, when we increase the temperature, we had some initial temperature and some final temperature. Then we had some change on temperature. Then what happened if the change on temperature is larger? Yes, if the change on temperature is increases, what happened with the heat? The heat will be also increased. Then this is why the heat and the change on temperature, they are direct proportional. Yes, more if the change in temperature increases, the heat also increases. And let's see what happened with the mass. And we already discussed that if we had more mass, we will have more heat. Yes, more mass indicate more heat. And this is why the heat and the mass, they are direct proportional. If we put this together, these two relations we had here, yes, if we put this and this together, then we will get this proportional. Yes. Then heat is direct proportional to the mass, but heat also is direct proportional to the change on temperature. If we want to write this proportional as equation, then what we need to introduce some constant of proportionality. Then this constant of proportionality is called the specific heat. Then as we can, if this will be the constant of proportionality, but usually in the books they write in the middle. Yes, this is. Then C is the constant of proportionality and is called the specific heat. Then what is the specific heat? What is C? Is the amount of heat or energy, now we know heat is energy, needed to increase the temperature of 1 gram of a substance in 1 degree Celsius. That's how much heat we need to increase in 1 degree Celsius 1 gram of that substance. Now we want to check what are the units of the specific heat. Then to do that, what we are going to do, we will solve for specific heat in this equation, and then we will see what units, what are the units of the specific heat. Let's see, first solve for specific heat, and we have this equation. Yes, we already got this equation. Then to solve for specific heat, we need to divide by mass, divide by change in temperature, and we have to do the same on the other side of the equation. Then the mass cancel out, the delta T cancel out, and then we had equals to, or you can write same thing. Now let's see what are the units. And we know the units for heat is cal, the units for mass can be grams, and the units for change in temperature is degrees Celsius. Then let's write units. And when we are talking of the units, we use brackets. Then let's for heat cal, for mass grams, for change in temperature degrees Celsius. And these are one of the set of units for specific heat. Then now we want to show that if we had this units is the same if we had kilocal over kilogram or degrees Celsius. And let's show these two units are equivalent. If we had this is the same if we had kilocal over kilograms per degrees Celsius. And let's start from this side. And we had then we know kilo means 1,000 or 10 to the power 3 is the same. Then we know we had kilo is 1,000 cal. We had kilograms is 1,000 grams. And then we had degrees Celsius. We can see this 1,000 and 1,000 we can cancel out and we will have at the end. Then we can see if we had this and these units, they are equivalent, they are the same thing. Then 1 kilocalories per gram per degree Celsius is the same as 1 cal per gram per degree Celsius. And these two are the same. And let me write here this 1 and let me write 1 here. Then we had the same thing. Then you can use either this Unix or this Unix. Then let's now check the specific heat for some substances. Then we can see, remember what is the definition of the specific heat is how much heat we need to increase the temperature in 1 degree Celsius for 1 gram of that substance. And you can see in case of the metal, we need less heat to increase in 1 degree Celsius 1 gram of that substance, yes, of that metals. But we can see in case of the concrete, let's see, for example, iron, we need 0.11. In case of the lead, we need really small amount of energy, 0.03. In case of silver, we need just 0.05. But in case of concrete, we need 0.16. Yes, and in case of the aluminum, is also a metal, but we need 0.22. We need compare with the, for example, with silver, we need about 4 times, yes, the amount of heat to increase the temperature in 1 degree Celsius per 1 gram. And we can see also the specific heat for water is 1. Yes, in liquid is 1, and we can see this is really the largest value compared with the other substances. Also, you can see here when we had the Unix for the specific heat, we can see if the specific heat for aluminum is 0.22 calories per gram per degree Celsius, is the same value if we had kilocalories per gram per degree Celsius. Yes, because we already showed these two units are equivalent. And you can use 0.22, this Unix, 0.22, and this Unix. Now, in this picture, we can see is how much energy need to absorb 10 grams of aluminum to increase the temperature from 20 degrees Celsius to 100 degrees Celsius. Means if delta T is 80 degrees Celsius. Then we can see in case of the aluminum, we had 176 cal need to absorb, yes, to increase that the temperature. Now, if we had the same mass in case of the copper, then what happened, and if we had the same change in temperature, what happened is the heat that is needed to increase the temperature from 20 degrees Celsius to 100 degrees Celsius for 10 grams of copper is just 74.4. It's less compared with the aluminum. But in case of gold, if we had the same mass, the same range of temperature, gold needs just 24 cal. Then the reason we had different amount of heat, yes, in this case, then the reason is the specific heat of the material is different. And we can see the specific heat in the gold is just 0.03. Yes. In case of the copper is 0.093, and in case of the aluminum is 0.22. Then this is why another variable we need to take into account is mass, change in temperature, but also the specific heat, which is one property of the material. Then let's solve one problem in which we apply the equation that correlates heat and temperature. Then we want to calculate how much heat must be supplied to a 500 grams pan to raise its temperature from 20 degrees Celsius to 100 degrees Celsius. If the pan is made of iron and if the pan is made of aluminum. And let's see what information we had. We know the mass for both pans are the same. Then we had the mass equals to 500 grams. We know the initial temperature is 20 degrees Celsius. The final equals to 100 degrees Celsius. Then we can calculate the delta T, which is final minus initial, will be 100. The delta T will be 80. And the other information we had from the problem is we know the material of the pan. Then we know the specific heat for that material. Yes, we know the specific heat, then we will use the table, table 4.2 in your book. Then the specific heat for iron, 0.11, and we will select this units. Yes, because we had the mass in grams, we had the temperature in degrees Celsius. Then we will select these units. And here will be 0.11. In case of the aluminum, then we had 0.22 calories. And now we can calculate the heat in each case. And let's start with the iron. How much heat we need to supply in case of the pan is made of iron. Let's start with that iron. We have mass, we have specific heat. Let's write in general the equation, then in this way we save some space here. Let's write here. In general, we have this equation is mass. And let's calculate case of the iron. And we need the mass for the iron pan will be 500 grams. And in this case, we need to multiply by the specific heat of the iron. Then will be 0.11. And then we need to multiply by the delta T, which is 80 degrees Celsius. Then if we multiply these numbers together, we will get 4,400. And let's check the units. Then we expected cal. Yes, this is the units we expected. Then gram cancel out with gram, degrees Celsius cancel out with degrees Celsius, and we have cal. This is the units we expected. And let's convert this one into kilocalories. Then in the problem doesn't say, but in some problems you had to calculate in kilocalories. Then and we know one kilocalorie equals to 1,000 calories. And this cancel out. We divide by 1,000, then we had 4.40, 3 significant digits. We have here 3 significant digits. Kilocalories. Then the answer can be this or can be this. And let's now calculate for aluminum. Then we had the same mass for the pan, but now we need to change. We need to multiply by the specific heat of aluminum, and then by the change in temperature. Then in this case, we had and again this cancel out with grams, degrees Celsius, and we had cal. And if we want to convert this one into just we divide by 1,000, then we will have 8.80 kilocalories. That's the same procedure we did before. And this is the answer in case of the aluminum, and this is in case of the iron. That we can see in this problem is because the mass is the same, the change, the delta T is the same for in both cases, just the amount of heat depends on the value of the specific heat. And we can see here the specific heat is twice, yes, the specific heat of the aluminum is twice the specific heat of the iron, and this is why the amount of heat that we need to supply to the aluminum is twice also. Yes, we had 4,400 cal, and here in this case we had 8,800 cal, or 4.40 kilocalories and 4.80 kilocalories. The next thing we want to discuss is heat as energy transfer. And the first thing is we need to remember the heat is one kind of energy. Then how we can transfer heat, or how the heat can be transferred. Then one way is if there is a difference in temperature. Yes, if we have temperature difference. Always the heat is moving from high temperature region to the low temperature region. As if we put some hot metal inside of the cold water, what is happening is all the heat from the metal is going to transfer to the water, and in some point will be the metal and the water will be in thermal equilibrium. They will reach up the same temperature. And the other way the heat can be transferred is gaining energy, but any way of the energy form, yes? Then can be transferred as mechanical energy, as radiant energy, or electrical energy. In this example, the heat is transferred as radiant energy. Yes, it's transferred from here to here. There are 3 different mechanisms the heat can be flowed, yes, or can be transferred. One is by conduction, the other is by convection, the other is by radiation. The conduction is transferred by direct contact. As you need to contact, or the two materials must be in contact to transfer the heat. The other is by convection. If this is due to the motion of the masses of molecules. Yes, in this case, the material must be flow, or the substance must be flow. In the third case is the radiation, and in this case the energy is transferred by electrical radiation. Let's start a little more about conduction. And we already said that the temperature flow from higher temperature to low temperature. This is the first thing. The second thing is what happened in the conduction. We know the objects or the substances must be in contact. Then in conduction, the energy is transferred molecule to molecule. Then in this case, what happened is, if we want to heat this tube, then, and if we use this flame, what happens is these molecules start absorbing energy, yes, absorbing energy, and they start vibrating. But after some time, this energy is transferred to another molecule, to the next molecule, to the next molecule, and at some point, all the molecules start vibrating faster. And this is why the temperature is increasing, yes. But because it's transfer molecule to molecule, it will take time to get the uniform temperature in the tube, yes. According to the efficiency of conduction, of the heat conduction, the materials can be conductors or insulators. Then in case of the conductors, they transfer energy very efficiently, and usually the conductors are metals. Yes. Then we had here the metals, but also we had insulators. They transfers the energy very inefficiently, and this is usually the base insulators. They had space, or more space compared with the metals between the molecules. There are more space between the molecules than the space you can find in case of the metal. But the best insulator is the vacuum, yes, because there is no molecules to pass on energy. Then here we can see that we had four conductors or good insulators is wood. Cotton also is wood insulator, but the base insulator is the vacuum. The heat can flow also by convection. And we already discussed that molecules with higher kinetic energy can move from one place to another place. Yes, this is the case of the liquid and the case of the gases. Also, in this example, if we had cool air in a room, when the cool air passed through the heater, the air became warm and then expand and is moving upwards by the cooler air. Yes. And this process repeat again and again and again until the temperature we want is reached. And same happen when we are boiling water. Yes, the water that is become hot, or is the molecules that have more energy are moving up by the cool molecules. Yes, and then this process repeat again and again until the water is boiling, for example. And this is why the heat flow by convection happens only in liquid and gases. because in this case, the energy is transferred by the mass motion of the molecules, and the mass need to move to flow, and that happens only in liquids and gases. The other way the heat can flow is by radiation, and in this case, this kind of heat flow involve radiant energy. Is the energy that can move through the space, to the empty space. Then radiant energy involve a series of radiations, and one of these radiation is the visible light. And you can see just a small part of the electromagnetic radiation. Then all the set of all this radiation is called electromagnetic radiation. Also, it's important to remember all the temperature above the absolute zero give off radiant energy. And any object, any substance, any body that the temperature is higher than the absolute zero temperature will be radiation energy. For example, we radiate energy in infrared region mainly, as in this region. And remember, the radiation is transferred by electromagnetic radiation. It can be any of this radiation. Yes, we will discuss each of these radiation in the next chapters. And let's now discuss energy, heat, and molecular theory. Yes, we involve all these concepts to discuss the phase change. Then we already say the motion of a molecule can increase by adding heating to a temperature difference, if that substance absorbs energy in any of the forms of energy we already studied, and also the temperature increases in some substance depend on the specific heat. Yes, depend on its specific heat. Then what happened in solids, we already mentioned. Let's review. In solids, we had organized structure, as we had something like that. The molecules can just vibrate. Yes, they can just vibrate, but they cannot move, they can't translate. Then what happened is, if we transfer energy to this material in solid state, what happens if we transfer energy, or if this material absorbs energy, then the molecules we had more energy to move. Yes, we will gain kinetic energy. And in liquids, it's not organized like that. Probably we had something like that. But the molecules not only can vibrate, they can always also translate a small distance compared with the size of the molecules, but also these molecules can rotate. In some point, what happened is the solid will be converted into liquid, and the melting process will happen. Yes, if the material is absorbing energy, yes, in this direction. And if the material absorbs more energy, then what happened is the molecules we had more kinetic energy. And the molecules now can move faster and larger distance. The translation, they can translate larger distance compared with the size of the molecules. Then in this case, the molecules can move larger distance, yes, like larger distance, can rotate, it can vibrate. In some point, what happens is if the material absorbs enough energy, then the liquid is going to transform into gas by vaporization process. If that material releases the same amount of energy, then the process will be in opposite direction, as gas can convert into liquid by condensation and liquid can convert into solid, and this process is called freezing. Then this is happen when the material absorb some energy, some heat, or release energy of some heat. There is phase change in that material. And in this picture, we had the phase change diagram. Yes, this is more or less what we discussed in the previous slide, but now we had the diagram temperature versus energy. And in this case, what happened is, in this direction, the material is absorbing energy. Then if the material is absorbing energy, the temperature will be increased, yes, because now the molecules of that material will start vibrating faster or moving faster. They will have more kinetic energy. Then what happened is, now temperature increase, but in some point, if the material has enough energy, then this solid will be turned into liquid. Yes, turned into liquid. Then, but what happened is, we can see here, even the heat, if the material is absorbing heat, you see from this point to this point, even the material is absorbing energy, there is no increasing in temperature. Why this happens? Yes, why if the material is absorbing energy, why the temperature is not increasing? The reason is in this case, all the energy is used to phase change. Yes, all the materials change the internal energy of the substance, and this is why there is no change in temperature. Once the material is changed from solid to liquid, then now if you give more energy, then again the temperature start increasing. Yes, so increasing, but now we have liquid. It's not anymore solid, we have liquid material. And what happens is that the temperature increases, but at some point, even if the material is absorbing more energy, again the temperature is not increasing. And why this happens? Because all the energy is used in phase change. The energy changes the potential energy of the molecules. Yes, it changes the internal energy of the molecules of the substance. Then in this case, the liquid is converted into gas. Once all the liquid is converted into gas, if you give more energy, if the material absorbs more energy, what happens is now the temperature starts increasing again. Then we can see there is some part of the diagram. We can see the material is absorbing energy and the temperature in the material is increasing. But in the points where the phase change occurs, there is no change in temperature because all the energy is used to change the phase. if we want to calculate the total amount of heat that is absorbed or released during all these phase transitions, then we need to calculate the amount of heat in each process, yes, in each of this part of the temperature heat plot. Then we know how to calculate the heat if there is change in temperature, yes, and we know we can apply this equation. What we need to know, we need to know the mass of the substance, of the material, we need to know the specific heat, and we need to know the change in temperature. Then in this portion of the graph, we can apply this equation. But what happened in those portions where there is no change in temperature, yes, like in these cases? Here we can see the heat is increasing, however, the temperature is constant, also in this portion of the graph. And we know in this portion what happens, there is a phase change. And this is why when the phase change occurs, then all the energy is used to change the phase, to break or to form new bonds. And this is why there is no change in temperature. It's all the energy is used to phase change. Then in this case, how we will calculate the energy or the heat? Then if we need to calculate the energy of this part when the substance changes from to solid to liquid, then we will use the latent heat of fusion equation. Then we will use this equation. With this equation, you will calculate the total heat involved in a solid liquid, or liquid to solid is the same number, just change if the heat is absorbed or is released. And we can see this heat depends just on the mass of the material, yes, and the latent heat of fusion of that particular material. Then this value depends on the material. In our case, we will use just, all the problems will involve just water. Then we need to know the latent heat of fusion of the water. Then these are listed in the equation sheet. You will find all the values for this constant. Then if we need to calculate the heat when the material changes from solid to liquid or vice versa, we will use the latent heat of fusion. If we need to calculate the amount of heat that is needed to change the material from liquid to gas, vapor, or vice versa, then we will use in that part the latent heat of vaporization. Again, the latent heat of this is a constant. This latent heat of vaporization, this is a constant and depend on each material. Then now let's review. We had the whole picture here. Then we need to calculate the amount of heat that is absorbed or released during phase transitions in this case. And how we will do that? Then the first thing, we need to calculate for each portion of the graph. What is the heat in each case? And in this part, there is change in temperature. Let's start in this and is finish here. We can see there is change in temperature. Then in this case, we will say will be equal to mass of the material, the specific heat of the, in this case will be the solid. Let's think we had water in our problem. This is most of the cases we had water. Then here will be, if this is the substance, if this is the substance we are analyzing, we will have here the specific heat for ice and delta T. Then we need to calculate the specific heat in the B portion of the graph. When we had here in this part, and there is no change in temperature. We cannot use this equation. And what we use, because there is from solid to liquid, then we'll use the latent heat of fusion. Then if we want, now we need to calculate in the C part of the graph, then there is change, again there is change in temperature, and clearly we can see there is some initial and final temperature. Then we will apply just this delta T, the change in temperature from this point to this point. Then in this case we will have the third, this part will be the mass of the substance, the specific heat, but here will be we need to apply the specific heat of water, yes, because it's liquid. I will just write here water, and then the change in temperature. Now let's calculate for the big part of the graph. We say D, that part. Then there is no change in temperature. We see it's constant. Then we need to apply the latent heat of vaporization. Then it's the mass times the latent heat of vaporization. And remember, these are constant values, and we will find this one in a table. There's this latent heat of vaporization and latent heat of fusion. And if we need to calculate in this part, then in this case we will apply, this is the last part, the mass of the substance. In this case will be the specific heat of the water, if this is the substance of the water, but in gas, or it's a vapor. And then we had delta T. And delta T is the change in temperature from this point to this point, yes, because it's just the last part of the graph we are calculating. Then to calculate the total amount of heat, what we need to do is just add all the 1, 2, 3, 4, 5. Let me change that. 3, 4, 5. And in some problems, you don't need to calculate, depend on the problem. Yes? Sometimes you need to calculate just the first 3 or just the first 2, depend of the range of temperature you need to analyze the problem. Yes? In what range of temperature you need to solve the problem. But this is the whole picture, how you calculate the total amount of heat that is released or absorbed during phase transition. And this is the graph is in your book, and you can see is similar graph. Yes, maybe now you understand what is the meaning of each of these equations and when you have to apply each of these equations. Yes, this is the graph is in your book, temperature heat graph. And this is the table 4.4, and this similar information you will have in the equation sheet. This is the specific heat for water. Water is 1 cal per gram per degree Celsius. For ice is 0.5, and for steam or gas will be 0.48. The latent heat of fusion for water is 80 calories per gram, and the latent heat for vaporization will be 540 calories per gram. It's more energy, yes, more energy to change from liquid to gas. It's really a lot of energy compared with the energy is needed to change from solid to liquid. And this, this one is the conversion factor from calories to joules. And again, this is the only constants we will use to solve these problems. This is the only constants we will need to know. It corresponds to water. Yes, we are not going to work with any other substance in this kind of problem. Then let's now try to solve this problem. Then how much energy does a refrigerator remove from 100 grams of water at 20 degrees Celsius to make ice at -10 degrees Celsius? And let's see what information we had. We know the mass of the water is 100 grams. The initial temperature is 20 degrees Celsius and the final temperature is -10. And we know one more thing is water. Yes, that is important information. And let's try to plot temperature versus heat to know what we need to calculate. And we had here the temperature, degrees Celsius. Here we had the heat. Yes. Then let's think here we had 20 degrees Celsius. And we know at 20 degrees Celsius we had liquid water. Yes, we had water, it's liquid. Then we had 100 grams of water, which is liquid. Let's start here. And now we need to make ice. Then the first thing is we need to decrease the temperature. Let's think we had here 0. Okay. And we need to decrease this temperature of the 100 grams of water. And here we need to stop because we know at 0 degrees Celsius something happened. Yes, in this case the water is changed from solid to liquid. Freezing happening in that case. Yes. Then we know when there is phase change, all the energy is used to change to phase change, and this is why there is no change in temperature. We need to represent that in the graph, and then we want to bring this water to -10 degrees Celsius. Then once the liquid is changed, the solid is liquid it changes into liquid, then we need to decrease this. Then now we know we need to calculate, if we want to know the total energy or the total heat that we need to remove from that water, then we need to calculate this, and this different heat. And at the end, we need to add to get the total heat that is removed from the water. We need to now let's think how we will calculate each of these, the different heat. Then here is the mass, a specific heat of the water because it's 20 degrees Celsius multiplied by delta T. In this case, just we need to multiply the mass times, the latent heat of fusion. And in this case, we need to multiply the mass times the specific heat of the ice multiplied by delta T. And now we know exactly what we need to do. What other information we know? We need to know the specific heat of water. We know is 1. The ice is 0.5. and latent heat of fusion is 80 calories per gram. And this is you will have in the equation sheet, also is in the book in table 4.4. And let's write these values here to know we need that information. This is 1 point. Ice is 0.500 and it's 80.0. Then this is all the information we need. Then now just we need to solve the problem. Now we understand what is happening, what equation we need to apply. Just now we need to calculate the different heats we need to calculate. And let's start with the first one. Then the mass, we are going to apply this equation. Okay, this one first. Then mass will be 100 grams. Let me write with the correct number of significant digits. It's 100.0 times will be 1.00 grams, and then will be delta T. And here there is one consideration is made in the book, is they consider always the delta T positive. It's maybe to avoid confusion. Then in this case, just we can see is what is the change in temperature, and we don't take into account the sign of the change in temperature. Okay, just the change in temperature. Other words, we will consider the delta T always positive. Then when we had any signs, when we calculate the heat and we had positive or negative, this means is if the energy is absorbed or is released. Then if the heat is positive, you had the energy that the substance gained. But if the energy is released by the substance, then the heat will be negative. But in this book, what they are doing is they consider just the amount of heat without considering the sign. And you will use your words to say if the energy was absorbed or was released. In this case, the energy was released, yes, but we are not going to indicate with any sign that the energy was released. Just we will use words. And this is why in this book, yes, the delta T will be always positive. Other words, we will take the absolute value of the delta T is always positive. And in this case, if we analyze this graph, the delta T from this point to this point will be 20 degrees Celsius. This will be the delta T in this. And this is important. I suggest you to make graph, yes, to graph the problem, because it will be easy to see what is the delta T. And the delta T is 20 degrees Celsius in this case. And let me write 20.0 times. If we calculate this value, we expect it in cal, and then we can see grams cancel out, degrees Celsius cancel out, and we will have 100 multiplied by 20 will be 2000. 2000 calories. And let's calculate the second. Then we're done with this. Now let's calculate the second part as this. Then the mass of the water will be 100 grams times the latent heat of fusion will be 80 in case of the water. And we can see grams and grams cancel out, and then we will have 8,000 calories. And now let's go with the last part. The mass of the water will be 100 grams. The specific heat of ice will be 0.500 gram per degree Celsius. And then the delta T in this case will be just 10 degrees Celsius. And in this case, we will have just 500 calories. And to find the total amount of heat that is removed from the water, and just we add all this, different amount of heat, then we will have 2,000 calories plus 8,000 calories plus 500 calories. Then finally, we will have here 10,000 500 calories. And now, if we want, or if we need, if you had to give the answer in kilocalories, and remember, you just divide by 1,000, or you can use the conversion factor, as you can say here also. And this is the answer in calories, and you can say here if one, that will write this one. Thousand. Let's cancel out. Then we divide by 1,000. Then will be. Let me go here. 2.5 kilocalories. And this is the answer in calories. This is the answer in kilocalories. Also, you can give this answer in scientific notation. Yes. And you can say it's 1, 2, 3, 4, and it's 1.05 10 to the power 4 calories. This is another way we can give the same answer. And there's all the different ways we can express the same answer. Then we can say here the amount of energy that is removed from the water is 10,500 calories, or 10.5 kilocalories, or 1.05 10 to the power 5, 10 to the power 4 calories. And we can see at the end, in the final answer, we keep the 3 significant digits. Yes, because we had here 3 significant digits in the information we had from the problem. Let me write here the line. Then this is the way we need to solve, is we can solve this kind of problem. And this is all I had to discuss in this case.